All right, hello everyone. This is 4.6 day 1, and we're graphing secant and cosecant today. And I'm going to come back to this top section after we look at the parent functions by hand, because this is kind of overwhelming to look at all that detail at once. But to give you a brief overview, notice that we have vertical asymptotes that are going to be separating these branches, and you'll have a branch pointing up and a branch pointing down, opening downwards. All right, so let's start off with the parent function, kind of walk our way through it, and then we'll come back and look at some of those specific details. So we learned that the secant function is the reciprocal of cosine. So these are going to be related in that we're going to use cosine to help generate the framework upon which we'll build the branches that we see representing that secant graph. Okay, so imagine for a moment that we are in fact graphing cosine, not 1 over cosine, but just cosine. So you recall that from the unit circle, looking at these quadrant angles, and just jotting a few of them down here. What we're doing is we're identifying the coordinate points on that unit circle. And we said that cosine is paired up with the x-coordinate. So when we were graphing the cosine function, we were looking at a certain angle, that's our input, and the output was the x-coordinate. So let's imagine for a moment that we're graphing cosine. So on my scale here, I'm using every other grid line here, so there's pi over 2, there's pi, 3/2 pi, and 2 pi. We know that from start to finish, we have 1 period of 2 pi. And on my vertical scale, again, let me skip every other grid line here, use that as a scale. When we're at 0 radians, the x-coordinate is 1. And then when we're at pi over 2 radians, the x-coordinate is 0. So this creates that V-shaped pattern that we've talked about before. Now I'm just dashing this in because this is not the final answer, but it will help us get our secant graph in a moment. So that's the cosine graph. Cosine is when we are plotting, the input is the angle of rotation and the output is the x-coordinate. Well, secant is the reciprocal of that. So what that means is we're not plotting the x-coordinate, we're plotting 1 divided by the x-coordinate. So at 0 radians, we have an x-coordinate of 1. So 1 divided by an x-coordinate of 1 is in fact 1. So this point happens to be at the same spot. At pi over 2, the x-coordinate is 0. So when we graph secant, we're graphing 1 divided by 0, and that's undefined. So what that means is we're going to have a vertical asymptote here, because there's no point to plot. At pi, we have an x-coordinate of -1. So 1 divided by -1, that also turns into a -1. So that's a real point that we'll be plotting in a moment. At 3/2 pi, the x-coordinate is 0 again. So 1 divided by the x-coordinate of 0 is once again undefined. So these are key landmarks that will separate the branches of our secant graph. So when we're graphing these by hand, we'll start by graphing the cosine function, then we'll figure out where the vertical asymptotes are, and then we're going to graph the branches based off of where these minimum and maximum points is. So you can see this minimum point here on the cosine graph. That creates this branch that is opening downwards. And then you see this point at the top where the maximum is on the cosine graph. That's going to create a branch that opens upwards. Now, if we just look to see what we have so far, we have these half of a branches, and that's a little awkward. We don't like to have half of a branch. We want to draw a complete branch. So we're going to copy this little half of a branch that's on the right-hand side and paste it over here on the left-hand side. So what we're describing as a complete period of cosine, which is from 0 to 2 pi, we are adjusting our window slightly, and so for secant, we're not going from 0 to 2 pi, we're going from negative pi over 2 to 3/2 pi. That's still a period of 2 pi total radians, but we want 2 complete branches. And that means we have, on the left side of this upper branch, a vertical asymptote here as well. So those vertical asymptotes are equally spaced out. So we're not graphing 2 branches and half of a branch, but rather we're taking the pattern of looking at this right hand and joining it with the left hand branch. So we have a complete branch there. And so we're saying that's our secant cycle length. Okay, so some of these other details. This then is 1 period. Again, that's divided into 4 intervals. So from the leftmost vertical asymptote, we jump to this branch, then we jump to the next vertical asymptote, then we jump to the peak of this bottom opening branch, and then we jump to this final vertical asymptote, and that's 1 period, that's 1 cycle. So once again, here is your axis on the cosine graph. This takes us up to our amplitude. Again, amplitude is always positive. And the height then, it kind of goes indefinitely upward because the branches go up forever. So that is going to be affected by, yes, the amplitude, but more accurately, the vertical stretch. So VS for short, vertical stretch. Now, one of the more complicated aspects of this is not the graphing, but the description of where do these asymptotes show up. We have vertical lines, so we can write the equation of a vertical line. So we know this is going to be x equals negative pi over 2, and x equals positive pi over 2, and x equals 3/2 pi. We want to write just one equation instead of 3 separate equations, so let's see how we do that. So here's the vertical asymptotes. It's always x equals because that's the equation of a vertical line. But what we're trying to do is we're trying to represent one equation that marks all the locations of all those vertical asymptotes at once. So there are 2 components to this. One is the spacing. How many radians is it from one to the next? So if I go from 1/2 pi to 3/2 pi, that's a spacing of pi radians. So that's the interval between one and the next. So we're going to say we have pi radians reoccurring. So this n is like a counting number. It could be 0, it could be 1, it could be 2 to represent like the first, the second, the third of those vertical asymptotes. What we're saying is at every spacing we have pi, of every spacing of pi radians, we'll encounter another vertical asymptote. However, we don't see one here at 0. The first one we see here is at negative pi over 2. So the first one, the negative pi over 2, is being added onto this equation. What we're doing is, I say it added on, but we're tacking it on. It's subtraction here because it's a negative. What we're doing is we're saying we're not starting at 0. We're actually shifting to the left a little bit. This is where we're starting, but then from that starting point, the interval is occurring every pi radians after the first. So pi radians later, we get to the next vertical asymptote. Pi radians later, we get to the next one. And if we were to keep on going, another pi radians, another pi radians. So this is the starting vertical asymptote, and this is the interval between them. So let me make that note here. This is the starting, or the starting vertical asymptote. And then this is the interval between them. So in this little tiny space, I'm trying to say interval between the vertical asymptotes. And we multiply that to the n, and n is just a counting number to indicate your first, your second, your third, and your fourth. And we can go on forever, and every pi radians later, you'll find the next vertical asymptote. So this is your starting. It's negative for us because that's where that first branch is plotted. And then this is the interval from one to the next, and that interval is equally spaced. So that's why it's going to be the same every time. Now, if you think about what we're looking at here, that is essentially what you saw up here. It was hard to keep track maybe of where the starting and where the ending of the cycle goes, but the idea is right here, this is your cosine curve. Right? So that's your cosine curve, and so at the peak of the cosine curve, that's where you have the valley of one branch. And at the minimum point of your cosine curve, that's where you have like the peak of the branch for secant. And they have a few extra parts of branches kind of thrown in there. So right here, that's the vertical asymptotes that we were just describing. So notice that we have x because that's how you describe the equation of a vertical line. Here they have pi over 2 as their starting, and then here they have n times pi. So the order is shifted around a little bit, but all of the pieces are there. This is your interval. Every pi units later, we see the next vertical asymptote, and then this is where they started counting. So that's a little bit different than what we have here. I put my pi times n in front, and I put my minus pi over 2 in the back because I'm starting here at this one. Let's take a look at the cosecant function. So the cosecant is the reciprocal of sine. So if you think about the sine graph that we had learned earlier, the sine function is a plot of the y-coordinates. We said sine is paired up with the y-coordinates. So again, here's my scale. So there's pi over 2, there's pi, 3/2 pi, and then 2 pi. And then on the vertical scale, same as before. So at 0 radians, we have a y-coordinate of 0. At pi over 2 radians, the y-coordinate is 1, and so on. We learned this pattern here. I'm, again, just dotting it in because this is not the final answer. But like before, we're not graphing the sine curve, we're graphing 1 over the sine curve. That means we're graphing 1 over the y-coordinates. We want the reciprocal of each y-coordinate. So at 0 radians, where the y-coordinate is 0, we want 1 over 0, and that creates a vertical asymptote. Now notice this one does start at 0, whereas over here, our vertical asymptotes did not start at 0. They were slightly offset. At pi over 2 radians, the y-coordinate is 1, so 1 divided by 1 gives me a real point. At pi radians, the y-coordinate is 0. So once again, 1 divided by 0 is undefined, so that's another vertical asymptote. And again, at 2 pi, we have another vertical asymptote. So notice that all of these vertical asymptotes for both of these graphs, they occur where my parent function hits the axis, right? So again, here is the axis of the sine curve. So I have 1, 2, 3 critical points on the sine curve. That means we've got 1, 2, 3 vertical asymptotes. On the cosine curve, my cosine curve touches the axis or the midline in just 2 critical points. That means we've got 2 vertical asymptotes to kind of separate. Now we have 3 altogether because of that left barrier, with that left branch being fully formed. But we're starting off with the 2, and those 2 are found when the critical values are crossing that midline, that axis. So that's what we're seeing here. So that means we have a branch opening upwards off of the sine curve's maximum value, and a branch opening downwards off of the sine curve's minimum value. And there you go. Notice we don't have a half of a branch hanging around like we did with the cosine curve. So we had to make a manual adjustment over here to make it look pretty so we could have 2 full branches. Here, we already have 2 full branches, so we're good to go. So here is 1 period, which goes from 0 to 2 pi. Again, that period is subdivided into 4 equal parts. So we're jumping to the bottom part of this branch, then we're jumping to the vertical asymptote, then we're jumping to the top part of the next branch, then we're jumping to another vertical asymptote. So again, we have that subdivision of 4 equal parts. There's your amplitude. Both ways, amplitude is always positive. And then beyond that, we really describe this as a vertical stretch, not an amplitude, as it goes indefinitely in that direction. And once again, we want to describe the equation of these vertical asymptotes. So it's going to be x equals, so there's two parts. There's the interval between them, and then there's the starting asymptote. So the interval, we're going from 0 to pi. We're going from pi to 2 pi, so that interval is 1 pi. So again, we show pi times n, meaning multiples of pi. 1 pi, 2 pi, 3 pi, 4 pi, and so on. Now the first one that we see is actually starting at 0. So you don't have to put a plus 0, but for the purposes of the notes, again, I'm just trying to show you that it's similar to what we saw over here, where you have the interval between the asymptotes, and then you have the location of the first one. Here, the first one's at 0, so you don't actually put a plus 0, but there's always those two components to consider. So there's your starting vertical asymptote. Those are the parent functions. Again, you take that back up to the information at the top, and you just see all these branches everywhere. Well, again, this is cosecant, which came from the sine curve, and that sine curve looks like this. Right, so there's the two branches, and then they have extra branches, because again, remember, the pattern extends indefinitely in both directions. Again, there's your equation for the vertical asymptotes. So these are some of the things that we've talked about before, like what's the period, what's the domain, what's the range. The domain looks a little bit strange, but notice the domain is essentially a limitation based on the equations that we've already found on those vertical asymptotes. Same with the secant function. The domain looks kind of crazy, but that's just what we already identified as the vertical asymptote. So you just take those equations and now you say, well, x cannot be those for my domain. In other words, my inputs can be everywhere else, but not these locations. So we're going to graph in this order. We're going to sketch the graphs for secant and cosecant functions in this order. First, we're going to sketch the corresponding sine or cosine. So we're either going to determine is it a cosine pattern or is it a sine pattern. We're going to graph that first. Then we draw the vertical asymptotes at the x-intercepts, and by that we mean where that cosine curve or the sine curve crosses the midline. Now if you have a vertical shift up or down, you have to look to see where the midline is, not the horizontal axis from the graph paper. And then the peaks to valleys, that just means, hey, that's where the branches go. I'm matching the peak of this branch to the valley of my cosine curve, or the valley to the peak. So the valley of my branch is placed on top of this peak on the cosine curve. Okay, so let's jump into our examples and look at how we can construct these by hand. Here's example number 1. We have a -2 times the secant of 4x plus 2. So again, let's identify our transformations. We have a, which is a -2. We have b, which is 4. There's no value of c because there's no horizontal movement in that case. There's nothing inside the parentheses, so the plus 2 is our d. So remember that the amplitude is always positive. So we take the absolute value of a, and then I just write myself a little reminder to remember to reflect this upside down. The period is 2 pi divided by b, right? Because what we're doing is we're saying, okay, I'm not graphing secant yet. I'm actually graphing its cosine, right? So we're starting off with the cosine curve to figure out where that goes before we graph the secant. So that's how we find the cosine curve, right? Cosine has a period of 2 pi, so it's 2 pi over 4, the value of b. And that's going to be my period. So then we're going to take that and divide it by 4. So remember, dividing by 4 is the same as multiplying by the reciprocal, so multiplying by 1/4. So pi over 8 is going to be my scale. So on each of these tick marks, I count by 1/8 of a pi. So there's 1/8 pi, 2/8 pi is pi over 4. Here's 3/8 of a pi. 4/8 of a pi is half of a pi. That was 4. Here's 5/8 pi, and then here's 6/8 pi, which is 3/4 pi. And then we can go negative as well. There's negative pi over 8. Where do we start and where do we stop? Again, we're thinking of the cosine curve. So we know that we take everything from the parentheses and we set it equal to 0 because that's where cosine normally starts. And we set that for x equal to 2 pi because that's where cosine normally stops. And we reduce that fraction. So again, this should make sense. If you're starting at 0 and you're stopping at pi over 2, that should match up the period, and it does. That axis or that midline, that's our vertical shift of up 2. That's the value of d. So y equals 2 is that equation of the horizontal line. So we'll come back to the vertical asymptote later. I tend to skip over the mins and maxes here, so I just graph them. So what we're doing is we are graphing the cosine function. So even though the equation looks like secant, we'll graph that in a moment, we start by placing down where does its cosine graph go as part of the foundation. Okay, so I have my axis, so that's at positive 2. I guess I should put my vertical scale on here. So how about 1, 2, 3, 4. So the axis is at positive 2. From there we want the amplitude. The amplitude is also 2, so 2 above that, and then 2 below that. That's the top and bottom of my box. We're starting at 0, and then we're stopping at pi over 2. So the technique that I've taught you in the past is to draw this box, and this is where one full cycle of the cosine curve will be placed. Now again, I'm going to dot this in because this is not the final answer, but our cosine curve is that V-shaped pattern, so we would expect it to look like this. Dot, 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 and so on. Okay? That's our cosine curve. However, we have to remember that we're actually reflecting this upside down. So we're going to take this V-shaped pattern and flip it upside down across that midline. Again, I'm still dashing this in because it's not the final answer. So you want to take a look at this upside down V. Now from here, we're almost ready to graph our secant function. What we've done up to this part is we've graphed this entire equation as if it were just a cosine curve. So that's what we did here in step 1. We sketched the corresponding cosine function. Next, we're going to draw the vertical asymptotes at all of those x-intercepts. Now, when we say x-intercepts, what we mean is where does my cosine curve cross the midline? This is my axis. So we're not talking about the horizontal axis, we're talking about the midline of the cosine curve. So that's these 2 points, here and here. So that's where I want my vertical asymptotes to go. And then between those, we're ready to draw those branches. So again, this is my upside down cosine. So here we have a maximum point on the cosine curve. That will be one of the branches of secant. And then down here where you have the lowest point of the reflected cosine curve, you're going to have these upside down branches. But we don't want half of a branch, we want a full branch. So we're going to take what's here on the right hand side, copy it, and paste it here on the left hand side. So there's my 2 full branches. So I want a barrier on the left of this branch that's opening downward. This will be the location of another vertical asymptote. So the cosine function was originally going from 0 to pi over 2. This is our viewing window, right? That's what the box is doing for us. But because we want 2 full branches, we're instead looking at this viewing window. Now it's still the same period, we just shifted it over, our viewing window shifted over. So the graph did not shift, it's just that we're looking at a different section, that's why I call it a viewing window. And there are your 2 full graphs. So notice here, we didn't start at 0, we started here at negative pi over 8. That will tell us where we're starting the vertical asymptote. So here's the equation. Again, there's 2 parts. There's where you start, so we could jot that down. We could go like this, negative pi over 8 plus. And then we want the interval between those asymptotes. So how far is it from negative 1/8 pi to positive 1/8 pi? Or you could say, how far is it from 1/8 pi to 3/8 pi? Well, from 1/8 pi to 3/8 pi, that's 2/8 of a pi. So 2/8 of a pi has to be reduced. And so we have to multiply that by n to show that it repeats. So one way that we could show it is much like this, the negative pi over 8 and then plus pi over 4 times n. Or if you prefer, we could switch those around and put the pi over 4 times n in front and then the minus pi over 8 in the back. It technically doesn't matter, but you need one of those that represents the interval between asymptotes, and one of those terms represents the starting point. And that's where we have our starting point. So you can see that drawing the upper branch and the lower branch is really pretty straightforward. It's like 99% of the work is just getting the cosine curve in the right spot. All right, let's look at a couple more examples going over to the next page. Here is example 2. We're looking at cosecant. All right, 1/4 times cosecant of x plus pi over 4. Now remember, cosecant is the reciprocal of sine. So we are pretending we're graphing the sine function. So the sine function is what we are thinking about for like the first 99% of what we're doing here, okay? So there's my value of a, which is 1/4, b is 1, c is a negative pi over 4, right? You always change the sign when you take that information out of the grouping symbols, and d is 0. Okay, so amplitude is positive 1/4. There's no reflection here. The period, we're going to take 2 pi and divide it by b. Well, b is 1, so it's still 2 pi. Take that result and divide it by 4 to find your scale. So pi over 2 is what I'm using on my horizontal scale. So 1/2 pi, pi, 3/2 pi, 2 pi. We can even go negative with negative 1/2 pi. We'll add more if we need to extend the graph further in either direction. Where does sine normally start and stop? Well, we take everything that's in the parentheses there, x plus pi over 4, and we set that equal to 0 because that's where sine normally starts. Get x by itself. And to find where it stops, take that x plus pi over 4 and set that equal to 2 pi because that's where sine normally stops. Subtract 1/4 pi from both sides. And once we make a common denominator, we get 7/4 of a pi remaining. So I need to figure out where that is because I'm starting at negative 1/4 pi, but I don't have a negative 1/4 pi because my scale is going at intervals of 1/2 pi. So we need to add in those fourths of a pi. So here is positive 1/4 pi, 2/4 pi, 3/4 pi. There's my 4/4 pi. Here's 5/4 pi. There's 6/4 pi, and here's 7/4 pi. And then going backwards, here's negative 1/4 pi. My axis is at 0. My vertical scale, because we have an amplitude of 1/4, that's going to represent it being vertically, flattened. So what I'm going to do is I'm going to count these off as like 1/4 of a value. So here's 1/4. Here's 2/4, which is 1/2. Here's 3/4, and then there's 1 full value. So each of my vertical grid lines I'm counting by 1/4. All right, so starting off with my axis or my midline, here's the axis of my sine curve. Now with the amplitude being 1/4, that means 1/4 up puts me here, and 1/4 down creates a very narrow band for our sine curve. We're starting at negative pi over 4, and we're stopping at 7/4 pi. So this is the box. It's a very narrow band, and we're going to put our sine curve here. Again, we're dotting it in because this is not the final answer, but sine would be on the far left-hand side on the midline. Then we jump to pi over 4, we're at the maximum. Then we jump to 3/4 pi, we're at the midline again. We jump again to 5/4 pi, we're at the minimum. And then we jump to 7/4 pi, and there we are back to the midline. So this is my sine curve. So that's 90% of the work right there, right? That's most of it. So now we're going to find those vertical asymptotes. So we're looking to see where does that sine curve cross the midline. So that crosses it here on the far left, here in the middle of the box, and thirdly here on the far right-hand side of the box. So now we look for the max and min points on the sine curve and draw the branches. One opening upwards, one opening downwards. And that's it. We're done with the graph. Now we're not quite done. There's one final step. We want to write the equation of the vertical asymptotes. And again, I'm kind of ignoring the minimums and maximums because we're just looking at the graph for those. But the equation of the vertical asymptote is going to be x equals something. So do you remember there's two components? One is what's the interval between one and the next? So how far is it from 3/4 pi to 7/4 pi? Well, that's 4/4 pi, which is 1 pi. So pi times n, meaning every pi units later we'll find another one of these. But where do we start? We start here at negative 1/4 pi, so minus pi over 4. And for good measure, here's one final example. Again, this is a cosecant graph, so one more time, we are looking at this as if we are graphing the sine curve. So let's pretend we're graphing sine. A is 1, B is 1/2, C is a negative pi, D is negative 1. Amplitude is just 1, no reflection here. Period is 2 pi divided by B. So remember, think of that as being multiplied by the reciprocal. So that's 2 over 1, and we get a result of 4 pi. So we take that 4 pi and divide that into 4 equal parts to get our jump, or the scale. So 1 pi, 2 pi, and so on. And negative pi on the left-hand side. All right, and let's see, where do we start and stop? So we're taking everything in the parentheses, x over 2 plus pi, and the sine curve normally starts at 0. We set this equal to 0. Let's subtract pi from both sides, and then multiply both sides by 2 to get x by itself. So we're starting at negative 2 pi. So let me add another negative 2 pi here on my scale. To find out where it stops, take x over 2 plus pi and set that equal to 2 pi, because that's where the sine curve normally stops. Subtract pi from both sides and multiply both sides by 2. So we're stopping at positive 2 pi. And our axis is going down 1, so minus 1 on that axis. With an amplitude of only 1, we won't see much of a vertical, well, there is no vertical stretch, right? So it's going to be a very narrow band here. So here's my scale of 1, 2, and so forth. So the axis starts us off here at negative 1. The amplitude of 1 takes us up 1 and down 1 space. So there's the narrow band where we'll see our curve. We're starting at negative 2 pi and stopping at positive 2 pi. So here's the window, here's the box for our sine curve. All right, so our sine curve, there's the 5 critical values. Again, there's no reflection, so that's our sine curve there. So then the next step is to find those vertical asymptotes. Again, we're looking to see where do the critical points cross the midline. So we're not looking on the horizontal axis of the graph. We're looking at the midline, or the axis of the sine curve. So there's always 1, 2, 3 critical points. So again, we have a vertical asymptote on the far left of the box, here in the middle of the box, and lastly on the far right-hand side of the box. Once we have those barriers set up, we're ready to freehand the branch opening up and the branch opening down, and there's our cosecant graph. So let's finish it off by describing the equation of the vertical asymptotes. All right, so let's think about this for a moment. Again, there's always 2 pieces. One is, what's the interval between the vertical asymptotes? So we're going from negative 2 pi to 0, or from 0 to 2 pi. So it looks like at every 2 pi radians later, we encounter the next vertical asymptote. So 2 pi times n. And then where does our first one start? Our first one starts here at negative 2 pi, so minus 2 pi. And that brings us to the end of the notes.